We did some tests on electric vehicle batteries in our lab. Um, Obviously, automotive grade 18650 cylindrical cells. You can see the test results here for the cycle life on the y-axis and utilization of state of charge or depth of discharge on the x-axis. You can see here quite clearly that, if you use less of the charge, no doubt 20-30% of the battery pack's charge, you will find about 5000 cycles, 3000 cycles, on an average maybe 3000 cycles, up to about 40% utilization. But the truth of the matter is, we are not using only this part of the utilization. We want to utilize maximum 70-80% of the charge, 90% of the charge. So that much depth of discharge is used in electric vehicles. At that time, you will find that the cycle life, charge discharge cycles, on an average is about 500 cycles. 500 cycles is very less. So on an average, if you draw the plot, dotted line, you see the average may be around 1000 cycles. They are giving you the, I mean, when you buy an electric vehicle, this means you are getting 6-7 years lifetime, which is fine on an average, 6-7 years lifetime. But why don't you make this plot more flatter? Like if I were to redraw this plot, I would rather have something here, straight line, not like this. Right now it is like this. Okay, so I don't want this part, and I would like to have this. This is something that will give sustainable cycle life over the battery pack lifetime. So this is one thing that we should look for. Okay, so that is what how you say a good battery management system will provide for your electric vehicle. So to do that, what do we have to do? Okay, so this, of course, all this work actually is in a publication, Transactions on Industrial Electronics. You can see the paper later. More details are there if you want. So what we need to do is identify the weak cells. What does a good BMS system do? Identifying the weak cell and redistributing the energy. So I will play the animation again. Redistribute the energy from the small cell overcharge and go to the large capacity cells. You need to identify all. So this can be done through machine learning, artificial intelligence, control techniques such as Kalman filter, extended Kalman filter. You have learned these things in theory in your courses, or you are also teaching these courses now, right? Some of you who are faculty who are teaching control systems have good knowledge of this, and very simply you can make an estimator. Okay, so this is what we have done in this work. Very simple. We have used neural networks. We have used other machine learning techniques such as nearest k nearest neighbor, regression techniques. Those who are in software, computer science and all may appreciate these techniques of computing and estimation, as well as combined with Kalman filters and extended Kalman filter for this work. So we redistribute, we identify the weak cell, and we identify the large capacity cell and redistribute the energy. Here is the animation of how the BMS works. So you can see the cells who are being balanced, voltage. Actually, how we measure the charge, it is a function of the open circuit voltage, the voltage of the cell. So once you identify the cell voltage that is low, then you can redistribute the energy from the low voltage cell to the large voltage cells. So we can balance all the cells together. So here is a balance scenario. You can see on the left hand side, we are balancing the cells. And how it is happening is shown here. Here is the BMS board, battery management system board, which is basically power electronics converters and passing the current to the cells. Here is the series connected cells in the module. One module of the battery pack is shown here quite clearly. So how do we achieve this? So coming to basic circuits, this also, again, fundamentals of electrical engineering, second year, actually first year engineering, second year, we talk about circuits, right, to our students. So this is something that is very fundamental. So first and foremost is a resistive equalizer. You can see DC circuit. Resistive equalizer is basically very common right now in our cell phones, laptops, etc. You will see this. Actually, this is actually being used, whereby you see series cells are connected in the electric vehicle, no doubt. The controller will, of course, turn on the switch. Suppose, let's say this one is the leftmost cell is being overcharged and it is having low capacity. So the controller will identify, estimator is inside the controller. So control signal is given to this switch, okay, and the switch closes. The overcharge of this one will be dissipated across the resistor because we have a common DC bus. You see the DC bus is common, okay, where the common point of coupling is there, and the over voltage is dissipated across the resistor. This is being used now. It is called a passive system. It is passive, you can see, okay, because heat is being generated also in the resistor. This resistor need to be sized accordingly for the voltage to be dissipated across it. So I square R loss is occurring here, and that is heat. So over time, actually, you must be careful how much heat you are dissipating. If the current levels are very, very high, see, that's why I call this the low cost. It is a low cost solution, no doubt. But if the current levels are high, like cell phone is fine, milliamps, laptop is fine. But if you're going into electric vehicles, larger energy storage units such as in renewable energy, etc., then you need to start thinking of active solutions. And that's what I'll talk about moving forward. Similarly, another low cost solution is capacitor, right? So if you have a capacitor which is suitably sized, you can balance the voltage. The over voltage in this cell, once the switch is closed, controller gives a command, then the over voltage can be balanced across the capacitor. It will charge the capacitor, which is also connected to the DC bus. And finally, the voltage is balanced with all the cells. So the idea is to have a common voltage of all the cells so that there is no circulating current between the cells. So they are balanced. What that does is basically enhance the lifetime of the pack by double. Theoretically, we can double the lifetime. And that is why I say that these solutions are very smart. Simple electrical engineering. It's not like something complicated. You can make this kind of thing for like few percentage of the pack itself. So this BMS system, this whole BMS system, this part, okay, or this, you can make it within maybe 1% cost of the pack. Let's say pack is about 100 rupees. You can make this for 1 rupee. So small, the power electronics, but that is a challenge. I am challenging you. Till date, even we have not been able to do. We are working with battery partners and industry partners, and their wish is that they want it within 1% of the pack cost. As you know, for any electric vehicle, the battery pack cost is more than half the cost of the vehicle itself. So suppose now, I mean, you have seen in the market, in Indian market, electric vehicle recently, see Mahindra Electric is there, E2O. You are having Hyundai Kona, latest Hyundai Kona electric vehicle, big SUV, right? It is a very expensive vehicle. And imagine inside that the battery pack itself is, and its systems, all the auxiliary systems of the battery is itself half the cost. So, I mean, if you can give double lifetime, and they say, oh, 8 years, battery pack will last 8-10 years. That is not good enough. I mean, who will pay after that? Okay, so like you will use, and who will buy the vehicle? Let's say you want to sell second hand. Electric vehicle you want to sell second hand. So who will buy it? Once you use 8 years, anybody will buy with the old battery pack? To replace the whole battery will be half the cost of the vehicle itself. It is not very economically sensible. So for that reason, I'm telling, if you can start making solutions around this BMS systems, the highlighted portion, and make it a very low cost, 1% of the pack cost, then you are in a business case. You can say, well, okay, I will give you, you can tell the person, they come to your workshop and say, this battery management system will sit inside your battery pack, on top of your battery pack, and give you 16 years or 20 years life, then for like little cost, right, 1% additional cost, you are making the money on this, but the owner has the benefit of double lifetime, which is fantastic. So please pay attention to simple solutions, right, not too complicated, and start building these solutions for the future. So these are some low cost configurations. When you go to higher currents, of course, larger currents such as in EVs, then you start looking at more active solutions like power electronic converters. Power electronic converters give you the advantage of actively charging the cells and discharging the cells as needed. So for example, this one on the left side, you can see high frequency transformer. Can anybody tell me what is this configuration? What converter is this? Oh, I mean, those who are in the area of power electronics, can you identify? No? So this is a flyback converter. You can see the diode, half bridge rectifier on the secondary side. Primary side is energized by a MOSFET, high frequency MOSFET. So quite clearly the energy is transferred by the high frequency transformer, and then the flyback converter converts the half bridge rectifier on the secondary side converts the AC to DC, high frequency AC to DC, to charge the cell. So what happens if there is an undercharged cell, right? These rectifiers will charge those cells and balance the cells across the string. This is a string of cells in series. So that is what the flyback converter can do. On the other hand, it is a costly affair because the transformer, high frequency transformer, is a costly item, right? It is a costly component in the power electronic circuit. So as I said, to achieve the goal of 1% of the battery pack cost, this converter we already built. By the way, all these topologies have been built, proven by us in our lab with our industry partners. They are happy with the solutions, but they say we cannot commercialize it. We cannot sell this product because it is not cost effective. Our customers will not buy it. Okay, so we had to scrap the idea. It is good for PhD and master's thesis and good papers, etc., but not for commercial product. So one thing I have learned in my last now I'm to 15 60 20 plus years 20 plus years of my research in this field is that what industry wants is the most important. Your research is one thing, which is good, but if you work with industry and industry driven research, then you start to appreciate the product, like challenges. You start to appreciate the challenges. Okay, so they said, well, this is not good enough. So we said, okay, we will go to a non transformer based, like can we do without transformer and big inductors? So okay, Chook equalizer, this is also a converter. Chook converter, many of you may be knowing already. It's bidirectional, like a buck boost topology, and having the capacitor as the energy storage element in between the two modes of operation. So generally speaking, Chook converter is very popular in chargers. Some of these Chook equalizers or Chook converters you can see even in your laptop charger. The box, the small laptop chargers which you see. Okay, so there are Chook converters being used in commercial applications as well. The idea here is it's quite simple. Two series connected cells you can see. Okay, like that there are hundreds of cells in series in the EV. Okay, each of these may be at a voltage of 3 volts, 3.6 volts, lithium ion cell. Okay, one thing is that is the Chook converter is the advantage is that the inductor holds the current constant. So therefore you can charge the cells with a very good quality current. So that is bidirectional currents on the inductors. So that is why we use this converter. So we pick the Chook converter as one of the topologies for our solution. Okay. But one more thing in this Chook converter is when we arrange it in the series, you see these series cells in the battery pack. Problem is again cost. They said, okay, we got the solution, It worked. We had a good, results. Okay, we got double lifetime, good calendar life, and as well as protection, etc. Because the capacity now is being maintained. All that was very beautiful, very nice. But cost, two inductors. See, one cell having investment of two switches, MOSFETs, and two inductors per cell. See the investment. So if I highlight just one part, okay, unfortunately, this whole thing is not economically feasible. For one cell only, you are investing four components, two inductors and two switches. In fact, most costly is the inductor. Okay, MOSFET is not as much, but inductors, yes. So imagine 100 cells are in series. I said, na, this is 3.6 volts, approximately 3.6, 3.8 volts. So when you talk about DC bus voltage in an electric vehicle, typically it is around 350 to 400 volts. That means 100 cells are in series approximately. So for 100 cells, if you are going to tell the owner, oh, I'm giving you this BMS system, but by the way, for each cell you need two switches and two inductors. It is a terrible investment. You will not face the 1%. You will not reach ever. In fact, when we built this, we came close to 10% of the battery pack cost. So if it is a $100 battery pack, you $10 is the battery management system, which is a large amount for a battery management system company or OEM to sell. They cannot make the business case. Okay, so that is one thing. Again, so we had to manufacture new BMS. So we built this, which is fine, but now we went for a further reduction in the components. So here you can see on the right hand side our new design. So from the two switch and two inductor module or configuration, we went to one inductor and one switch. Okay, and how do we achieve that? In fact, reduced parts converters is a research area in power electronics. How to achieve the same performance with small amount of components? It is with smarter control systems. Okay, so we have made more smart and more accurate estimation technique so that we don't need so many components to do the job. Okay, one inductor, one switch does the job. In fact, we have a US patent pending, so I cannot reveal much more details than that, but here is the configuration. So we started to do that, and for 5 cells we can do 5 cell voltage equalizer was built. So such 20 boards are required. Think of PCB board, PCBs, sorry, printed circuit boards were created for 5 cells. So 1, 2, 3, 4, 5 cells at a time can be balanced. 5 cells at a time. So if there are 100 cells, you need 20 boards. Okay, so that is the investment that you need to make. Here is actually the prototype. So if you always, build, you need to build the prototype. So the prototype was built using microcontroller for the control algorithm. Here you can see the MOSFETs. They are very small. Obviously, you don't need much investment in MOSFETs. The biggest parts are the inductors. You see, these are planar inductors which sit on top of the PCB. The inductors are the biggest investment, as I said, or cost in this board. Finally, the connection to the cells, 5 series cells, and the communication bus to the vehicle controller. The whole EV system has to be controlled. So communication has to happen between the battery pack or the battery management system and the overall electric vehicle controller. So we have also, the work actually started with how do you design be good BMS. So it starts with a good open circuit voltage estimation technique. So first of all, with an equalizer model, the cell model. This was picked from this paper by Professor Rincon Mora from Georgia Tech, very popular model. In fact, as you can see, this is depicting the cell. So if you were to draw the, the cell characteristics, this model will depict that one, open circuit voltage. So if I just show you open circuit voltage characteristics. So if this is voltage and this is current, typically for lithium cells it is like that, correct? Here is a transient, this part and this part. This part, hopefully you can see my drawing on the screen. So this is the operating region where the voltage is linear, straight line. Okay, that is the important part. These are no operation parts. Okay, where these are the transient parts. Transient. So these things are, as you can see, this characteristic like this, convex and concave curves can be modeled by these RC circuits. Okay, and all the linear portion, the linear portion, which is this one, can be modeled by voltage drop using internal resistance and open circuit voltage. This open circuit voltage here, this value VOC is of importance to us. But as you can see, it is internal. This voltage is internal to the cell. How do you estimate that open circuit voltage? Based on total voltage. You can measure here across the cell. This is the terminal voltage, VT. Okay. If you measure the terminal voltage, how to estimate this voltage is the key. And this can be done very easily, in fact, using Kalman filters, okay, or any other machine learning techniques that you may find interesting in literature. So this is another area of research you can embark on. Like, in fact, we even did projects with final year students. Small project like this can be proving that estimation techniques are important for estimating the open circuit voltage. Okay. So here you can see experimental results. You can see the cell modeling results versus experimental data. And this is on the real, cell. 18650 means configuration of 18 mm by 65 mm cylindrical cell. It is a real automotive battery electric vehicle cell. Okay. And you can see the open circuit voltage and the internal resistance. Here is the error in the measurement and our modeling results. Small error, you can see 0.1%. Here are the experimental results of the balancing. So we put this in our balancing circuit, the control system, and we found out that one of the cells we have unbalanced. They are coming to, so you can see the current coming to the 0 and voltage rising. Sorry, there is again some audio. Preeti. Yes, thank you. If you can unmute, yeah, please mute your audios. Of course, mathematical model versus experimental data is also very important. So you can see here the math model, which is simulation model, the orange one, and again experimental data. So this is very important, the experimental results. So as I showed you in the previous plot here, you can see this is the current value, which is being balanced with all the balanced cells. 4 cells are balanced, and the 5th one is being balanced by the board that I showed you, okay, that we built. And the voltage is rising slowly to balance the voltages. So once all the voltages are balanced of all the 5 cells, then there is no current flowing through the cells, between the cells. So there is no dissipation of heat. Zero current means 0 I2R losses between the cells. Therefore, now you are avoiding the catastrophic effects and saving the calendar life of the cells. So the amp power capacity can be conserved. Very important result, this result actually. Okay. And this all is matching with the, as I said, with the mathematical model as well that I proved before. So therefore, this is again the current which I took from the same previous plot. This one, the pink one, and this is the voltage. Okay. Current on left hand side, voltage, open circuit voltage on right hand side. So you can see the results matching the mathematical model, the orange one. Very important. So before you do the experimental, obviously you need to do the mathematical modeling and the simulation. So the simulation results and experimental results are matching quite clearly. See, accurately, transient as well as steady state. You can see here. Efficiency of our converter is around 90%, between 85 and 90% for 10 watts of power transfer between the cells. So between any two cells, I took first and second cell. Between two cells, the typical power transfer is about 10 to 15 watts. Okay, so that is our efficiency range between 85 and 90%. You can increase this up to 95% also. In fact, more recent work in our lab is being done on this aspect by using soft switch converters, by using GAN switches, MOSFETs, etc. So you can increase the efficiency of the converter. Then second part, of course, for this BMS is the charging algorithm. Inside the cells, how do you maintain temperature? The BMS is important, but how to feedback the temperature? So a new constant temperature, constant voltage charging algorithm was devised in order to have cells charging in a healthy fashion and implement it with the BMS. So second, just next 10-15 minutes, I want to talk about this. Two of our companies, eCamion and DNV Electronics, are working with us along with federal funding from NSERC, as I said earlier. These are some of the individuals who worked on it: Dr. Lalit Patnaik, Dr. Vinicius Marcis, and Dr. Praneeth Jayasai, who worked on these aspects. Again, this work has gone into products in DC fast charging systems. And as you can see, what happens inside the cells. So between all the cells which are balanced, which is fine, but the faster you try to do that balancing, the low number of cycles will happen. In order to maintain the number of cycles with fast charging, again, you need to have temperature conscious or health conscious systems. Here are some of the techniques to do that, existing charging algorithms within BMS systems. First is the constant current, constant voltage charging, and I will talk about this little more in deeper in my next lecture tomorrow. Similarly, you can have multi-stage charging, you can have 4C, 1C CV, pulse charging, sinusoidal pulse charging. There are so many ways, but these are the most popular techniques. But most of these depend on the manufacturer's data sheet, and they do not adjust for the aging or temperature of the cells. Once temperature increases, in fact, popular literature, if you read papers, more last 2 years, 3 years papers in IEEE transactions and conferences, you will find most of the literature and data stating that if the temperature, in fact, even if you buy cells from Samsung, LG, Panasonic, lithium cells, 5 degrees Celsius, 6 degrees Celsius rise will cause catastrophic effect on the capacity of the cell. The cell capacity reduces by 15-20%, which is huge. As you saw, for our BMS, it is more work to balance those cells. So temperature conscious battery management is very important. So most of these methods that I showed that are used for charging these cells, they are very conservative in nature. They depend on that data sheet, and they are very restricted by the temperature rise or temperature rise or delta T, which is gradient, temperature gradient, I should say, compared to the ambient temperature. So we need to keep it as close as possible to ambient temperature. So cell degradation occurs due to the uncontrolled heating. Typically, when we charge these cells, cell degradation is occurring. Degradation means, again, state of health. State of charge I talked about, which is our open circuit voltage function. Degradation is a temperature function, depending on the temperature. So the temperature has to be controlled in a fashion such that amp hour capacity is maintained constant. So what profile then ensures the fastest charging time and without hampering cell life or health is the question, the research question. So here we devise the new constant temperature, constant voltage charging algorithm. What we have done is we have increased the temperature very fast in the beginning, but we have flattened the curve to be constant till the same temperature rise as constant current, constant voltage. CCCV is a very common technique for lithium cells. CTCV is our technique. What we have done, we have, see, you can see in CCCV, because of constant current till reaching the open circuit voltage, you keep the current constant, such that the temperature rises slowly, very latently, and up to a maximum temperature allowed by the cell manufacturer. In constant temperature, constant voltage, we increase the step. It is a step rise and keeping the temperature constant. Then finally reducing, just like CCCV. We go to CV mode of operation, constant voltage. So in that way, by increasing this step of temperature, we can get a very high current at the beginning. That means you can charge your cell faster. So you can get ultra fast charging and same temperature rise as CCCV. So we have utilized this shaded portion which was available for high step rise of temperature and keeping it constant after some time. So you can customize this profile for each cell, and you can use current profile that can adjust for cell aging. Okay, same temperature rise and ultra fast charging. So these are the advantages of our technique, and this was for the first time in the world that this was introduced. Nobody had actually used a temperature feedback. So simple temperature feedback with a PID controller can do this. Again, it is not it's nothing, it's just simple control systems and using or utilizing your knowledge of the lithium ion cell, okay, and the charging profile. So what we do, lithium ion cell is there, temperature is fed back, sensor, obviously you need the temperature sensor to sense the temperature and feed it back to a comparator. The comparator gives errors and that error is fed to the PID controller. PID controller, of some of you will appreciate, temperature is not a very fast time constant. It is a large time constant, usually in terms of minutes. So when you're dealing with temperature, PID control is more than enough. Okay, so that current which is coming out of the PID controller command can be put through a summer. Your charging algorithm, which is here, I'm showing you the charging algorithm, is a feed forward. That feed forward source is added in the summer. Summer is there for the PID controller output and the charging algorithm. That finally is given to charger and that is given to the cell to charge the cell. So it works in a loop, keeping the temperature under control of the temperature rise, rather delta T. Okay, set temperature is there and this feedback temperature. So delta T is kept under control. So we are doing at cell level now. We are thinking of going to the pack level. Okay, same methodology to the pack level. Again, we are working with our industry partners on this, DNV Electronics as well as eCamion. So here are some results you can see here for the current profile, the voltage profile, and black one you can see temperature. See constant temperature you can quite clearly see. Okay, so we are using thermal model, second order thermal model, which is from 4J 2010 paper, and this Gao, Chen and He, they have 3 papers on 2002, 2006, 2011 of this electric model, electric circuit model of the lithium cell. So 2 models which we use, very simple models. Here are the parameters. Okay, we are using a Samsung 18650 cell. So this is experimental setup. You can see the experimental setup. Okay, here is the experimental setup in detail. Here is the block diagram of the experimental setup from our controller diagram, and here is the experimental setup in the lab. So you can quite clearly see the sensor here. Here are the battery specifications of the Samsung cell. Here is the discharge test. We have a reactor, Ternigi, from a company called Ternigi Reactor. They are giving us this discharge setup. So you can put the cell inside this discharger and you can discharge up to 20 amps. 20 amps means almost 10 times the rated current you can discharge. Okay, here you can see the experimental results for the discharging. So once we prove our algorithm of fast charging, so you can see here fast charging current as we did in the theory, experimental result shows you the same. So 2C rate we are charging. Okay, 1C is here, which is 2.3 amps, and 2C means 4.6 amps. So you can see we have gone up to 4.6 amps. This result on the right hand side bottom is showing you how much time you can reduce in charging. So 20% charging time has been reduced. Temperature rise we maintain, as you can see, constant at 7.5 degrees Celsius. This is below the allowable. Allowable is usually 9 degrees Celsius, 8 degrees 7 to 8 degrees is allowable. So 7.5 is within the limits. Okay. The blue one is the constant current, constant voltage. Red one is the constant temperature, constant voltage. CTCV, our proposed technique. So you can see temperature rise is the same as CCCV, but you are getting 20% faster charging and the voltages are equal. You see open circuit voltage obviously is being maintained. Then we did another test. This is just the data from that same test. I won't go through these details. At a 20% lower delta T can be achieved, okay, if you have same charging time. In order for the CCCV to have same charging time, we had to increase the CCCV by 25% current. So almost 3 amps, you can see, we increase CCCV, which is the popular technique. We keep our technique at 4.6, which is 2C rate. 7.5 degrees Celsius is maintained, but by increasing 25% of the CCCV, what we noticed that 9.5 degrees Celsius is the temperature rise. Means a whole 2 degrees Celsius more than our technique. Yes, no doubt the charging times now are the same. Okay, but we have at the expense or the cost is that you are paying is 2 degrees Celsius rise. Now you are going over 8 degrees Celsius. 8 degrees Celsius is the cutoff. 9.5 you are going. As I said, every degree Celsius, forget 1 degree, 0.1 degree, 0.2 degree, we have seen capacity fade going down, like 10% fade in the capacity. So those BMS that we showed you earlier, that I showed you, is so important now. This algorithm should be fed into the BMS so that you can keep temperature also under control, such that the catastrophic effects because of capacity fade do not occur. Once capacity fade occurs, as you saw, short circuit can occur. Okay, and by doing this 2 degrees rise just for the fast charging, like now the Tesla supercharger is there, you know, they say, oh, we can charge electric vehicle within 5 minutes, 5 minutes, 10 minutes. Great, no doubt, great. But what you are doing to the battery, and the BMS cannot handle that. So our BMS, which we are building, is incorporating this algorithm, which is very important. This algorithm is so important, you cannot value it in terms of dollars. In fact, it is so important. You can make a business case by integrating this temperature control algorithm along with the BMS that I showed you earlier. Also fast chargers, which I will talk tomorrow in tomorrow's lecture. Then of course, good cooling such as air can keep the temperature closer to ambient temperature and help in reducing memory usage in terms of the algorithm. So you can have a very efficient system, okay, with good cooling. So these are 3 results showing you can improve the charging time even faster with good cooling. Okay. Secondly, more important is the sensorless operation. I'm using temperature sensor, LM sensors, but unfortunately the sensors, like I said, there are 100 cells in series. Okay, and that is only 1 string. Suppose you want more current, then you need 2 strings. That means 200 cells. So 100 cells in 1 string series and parallel second string of 100 cells. So 200 cells, 200 sensors. Then the wires. Imagine the wires cabling for those sensors connected to hardware. So this is going to be cost. Again, our industry partners, we are working always with industry, so we can appreciate this. What we have started to work is on sensorless or machine learning techniques, estimation techniques to estimate the temperature on the surface of the cell. Rather than measuring, now we can have like an open loop sensorless operation so that the feedback is given to the controller without sensors. Okay. So what we have found is a 1.4 degrees Celsius error. You see the results. We have results here. These are experimental, measured result and the estimated result. The blue one is estimation. But as I said, in terms of temperature rise, here this temperature rise is only 7.5. Okay, 7.5 degrees Celsius. In that the error already I am getting 1.4, which is very large. So our efforts ongoing. And in fact, right now I'm looking for PhD students to continue this work. There are 2 students who are already working, PhD students, but this work will never end. Like It's ongoing. We need a couple of more PhD students on machine learning or control system who are very good at control to do this estimation work for us. So we are working with our industry and the partners are looking to hire these students. So the advantage of working with industry is something that this technology or this research feeds directly into the product. So they directly hire our students. So that is an added advantage, obviously, for the students. So yeah, reducing this error to, let's say, almost as close as possible to 0 is the key. So these are some comparison with the other charging techniques. This is our own battery test system we have developed based on our work. So we can test cells. This is the cell, battery under test, and around that is the hardware we have built. So here are some components, power supplies, etc. Sensor, you can see temperature sensor, analog measurements such as from the chroma system to measure. Here is the test system that we built. So you see temperature chamber is a very important aspect. So Vinicius is student from Brazil. He graduated recently. He found a job. We are using this temperature chamber, which is between -40 to 125 degrees Celsius. Here is a camera placed inside the chamber. So you can see the cell that we are testing inside. Our algorithm is being tested. You can change the temperature and check for our algorithm working. So his thesis actually is available. You can see the thesis and some papers also. We have, of course, here you can see this paper in ICIT conference in Argentina. We presented earlier in March 2020. Okay, it is for NMC cells, nickel, manganese, cobalt, lithium cells, 18650. These are from Samsung, the same types that go in the Tesla electric vehicle. Okay, so these are those cells. So you can see the results in the paper. Here is the sensor, thermistor assembly. So just summary, of course, we developed some smart charging schemes which can be integrated into fast chargers or in BMS. 20% less time with same delta T or 20% lower delta T with same charging time as CCCV technique. This I showed you. So given amount of degradation can be controlled. It also enables control aging and degradation, and simple PID controller with feed forward assistance can be used. Other projects we are doing, Yashwant actually also just recently graduated. We worked on some supercapacitor bank switching. Okay, instead of using batteries, here you classically supercapacitors were being used with batteries. Okay, in parallel to help the battery such that it can manage the energy of the battery and increase the lifetime. Supercapacitor is a power device, as you very well know. This is Yashwant's hardware on the right top side, right hand side. Schematic is over here at the bottom, right? So instead of using batteries, we eliminate the battery and only use supercapacitor bank. So one main bank and one auxiliary bank, the pink one here, switched with a smart switching scheme. You can switch the capacitors to get energy. Okay, so you have power and energy, both. So we are trying to eliminate batteries for that. This has been accepted in the transactions on transportation electrification. In fact, the paper is already out. I think we already have a volume and page number. It has been published already. Apurva Kelkar also just recently graduated. Apurva worked on testing and characterization of high discharge of cells, battery cells. This was initiated by our industry partners eCamion and Nova Bus and Volvo. Volvo buses, we are using the bus data to characterize these cells. So we got some cells from them, and they basically wanted to prove the, how you say, high discharge, 20 times the rated current of their pack. What they were doing was taking the bus, electric bus, and driving around a circuit, a track, simply driving and burning the cell. Because the bus is so heavy, electric cells, electric batteries discharge at around 20 times the rated current. 20 times rated current is not a joke. Like each cell is rated at 20 amps. So each cell at around 40 amps. Imagine all the cells going at 40 amps at 400, 600 volts, the power that is dissipated. So that was killing their battery pack. They said, can you build for us a test system, simple test system that we can test discharge of our cells. So this bidirectional converter, as you can see, it is having regenerative capabilities. So half bridge on this side and half bridge on this side. So it's half bridge power electronic converter, a simple solution during charging and discharging. 2 quadrant converters forming a 4 quadrant bidirectional converter. Here you can see the schematic. Okay. So what we do through using this converter from this cell, you can discharge at 20 times the cell current into another battery pack, or even better, maybe super capacitor. Here you can use super capacitor also. You can replace the battery pack with super capacitor. You can also power this battery using this converter into the grid. Single phase. You can configure this converter as an inverter. And from DC, you can convert to AC and power it into the grid. But the grid means you will have some problems with transients. Okay. That is the problem. And synchronization problem may occur with grid. Those who are in power electronics field will appreciate that one. Synchronization problem, but that also can be solved. But better still, you can use super capacitors or batteries on the secondary side, on this side, sorry, on the battery to battery or battery to super cap. So this is also ongoing work. Apurva finished one hardware, he built the hardware, and now there is ongoing work with other students. Because of our work, we have been selected to build Canada's first electric vehicle. Canada obviously has American subsidiaries such as Ford, GM, Chrysler, Toyota. We build in electric vehicle, we build in Canada, but Canadian built, there is no such vehicle from Canada. Okay, so Canada's first electric vehicle, we are the phase 2 project lead. You can see different designs here, 1, 2, and 3. This one was chosen. You can see the sketch, and this is the electric vehicle that is going to be built. It is called Project Arrow, and Ontario Tech has been selected as the lead for the design and construction of this vehicle. Our partners are McMaster University and University of Waterloo in Canada. Okay, along with Automotive Center of Excellence and engineering faculty, we are building. So for myself, I was chosen as the lead for the energy storage and charging part of this vehicle. Okay, so phase 2 will be led by us. In the next year or so, we are going to build this vehicle. Other ongoing work, you can see our team here. We have built race cars. This is a Formula electric race car, and this competition is very popular. Formula SAE, Society of Automotive Engineers, electric race. So Formula SAE electric is a brand name. And you can see the BMS that we have built in our own lab. You see the cells here, 18650 cells. Okay. In fact, these are 21170s, not 18650. 21170 means 21 by 21 mm by 17 mm. Okay. 21 by 17 mm. So this is the cells, and these are the BMS built by us. This is, of course, all 3D printed in our own lab. So all the 3D printing solutions also have been integrated in here. In fact, this has channels for liquid cooling or air cooling ducts inside this infrastructure. Inside this thermal management system is integrated. So the thermally, you can have air cooling inside these cells. Okay. Here is a picture on the bottom left in the Automotive Center of Excellence, the chassis of the Formula car. See on the right hand side, you can see with the team, this is the first car that we built as of 2019, last year. Then today we have this car, 2020, new version 2 of the car. You can see more slick and more compact. And here is the chassis on the dynamometer. You can test it for the race profile. So from outside on a computer, we can feed again, somebody have the Mayur. Can you please mute? Sorry. Thank you, Mayur. This dynamometer can emulate the behavior of the race profile. Okay, so you can test our systems. all the battery, the motor, the inverter, traction inverter, etc., the BMS functionalities. So before going into the race, we are already prepared. You can see ACE, this is Automotive Center of Excellence. So it's the same dynamometer you see here on the right hand side. So this is a GM Chevy Volt electric vehicle, which is being tested inside our Automotive Center of Excellence. Like we can even create the snow, minus 40 degrees Celsius, and see how the battery is performing. Or you can go to 125 degrees Celsius and see how the battery is performing. Here we are testing electric bus. We work with our partners, electric bus partners, as I said, Volvo, Nova Bus, and this is being bought by Ontario Power Generation. So this electric bus is tested on the dynamometer for how the battery is performing. Okay. Here you can see more recent. As of earlier this year, January, we didn't have COVID at that time. So Prime Minister, as you can see, those of you who can identify, the Right Honorable Prime Minister of Canada was at our own facility in our lab announcing $35 million facility for electric bus research. So we are now working more closely with our partners on e-bus applications. Okay, so that was helpful funding from our industry partners. Here you can see the microgrid in our own campus. So just a small tour of our campus. Those of you who cannot make it to Toronto, this is a small little tour. Microgrid obviously is a $7.5 million project. This is main lead is Panasonic, but GE supplied the solar panels. You can see solar panels. Hydro One, which is utility company, Oshawa PUC, or utility company, and Ontario Province Ministry of Energy gave the funding. Of course, the industry partners also have cash and in-kind contributions in this. As you can see, the Panasonic batteries are 500 kilowatt hours. Okay, so that is an in-kind contribution from our company. Same thing with the solar panels from GE, in-kind contributions. These are fully functional microgrid, first microgrid in Canada on a Canadian university campus. This is, we are proud to say, Ontario Tech is the first campus in Canada to have a fully functional microgrid of our own. And the pioneers of this, I must say, it is not my work. This is Professor Tarlochan Singh Sidhu and Professor Vijay Sood. Their work actually was the fruit of their efforts. Okay, I of course use this facility for developing my chargers. Tomorrow I will show in the talk how we are using our microgrid for EV charging. Okay, students can actually collect real data. It is a living lab, right? It's basically a living lab. So here is another view of the distribution system or the station, substation, distribution substation with isolators, circuit breakers, and also the transformers connected to the grid. We are connected to the local grid from these transformers. Okay, so the microgrid, this is another view of showing the system. And here is the SCADA system actually, which we are on the Oshawa PUC SCADA. You see at the bottom, the battery packs and the renewable energy system connected to the AC grid, main line. So this is the single line diagram, and this is the real SCADA system. So they can keep on monitoring our performance and the parameters of the batteries, energy storage, solar, pumping into the grid, or the batteries being charged from the grid, from the solar, so on and so forth. So these are some real data we can collect once we are operational, when the grid is operational, microgrid. So really I want to end my talk here. This is the last slide. This is our research fields. As you can see, the steer group, I introduced the group to you. We do everything from grid till motor in an electric vehicle, including the charger, battery energy storage. We focused a little bit on BMS today and power electronic solutions. We also do a lot of electric machine design and electric drives, which is not part of my talk. Obviously, there are other talks in this FDP. FDP, you will learn so many things. Today, my talk covered only the BMS part. But if you want to see or reach out to me for other aspects of the research, please do reach out. I will be more than happy to provide you with papers or reports or thesis which are available online from our group. So I will end here. Brushali ma'am, thank you very much, and all the listeners and audience, thank you for your attention. We can take maybe